if you don't have any questions, I'll probably start with today's introduction of Docker and containerization, why we do it, uh, where it helps, and especially if you're selling something, if you're selling a product or your process, why containerization of packages is important. So first of all, Docker right now is paid. So as we start Docker, we say Docker is cross platform, right? So but we will have playing environments from bigger players pretty soon. So Docker is not the only one. But as our session is around Docker, Docker provides a way to package applications, right? How you package an application. Uh, when you package something, you obviously can transport it to different places. So we can transport our applications to different environments, right? Now, Docker containers are based on Docker images. Docker containers are based on Docker images, right? So why do we use it? For portability and obviously resource efficiency, and to keep it separate from dependent resources, right? So it's called as isolation, but in simple English, I'm trying to tell you that when you package something in Docker, the isolation improves vulnerabilities, so security is improved. Same host, different host doesn't matter because it is isolated. Then obviously you are porting it, reproducibility is important, so you can have your Docker file created that you know what is happening with your application. Similar introduction to Kubernetes, orchestration platform, which can automate your scaling and then your management of containerized applications, right? So it is an orchestration too. And what are we orchestrating? Our containers, right? So basically, we help in, for example, that amount of money you spend on VMs, you end up spending lesser amount of money on Kubernetes VMs. End of the day, they are VMs, but cost saving is also, apart from scaling, cost saving is also very important. And then load balancing is what is very easy with Kubernetes. You have built-in mechanism, right? And as on the first day, we spoke about self-healing. Kubernetes is a very good example of self-healing, right? So as simple as restarting failed containers is self-healing, right? So we are connecting our dots. And then obviously when we talk about Docker and Kubernetes, resource management, isolating and scheduling is an important, you can find it on Google, but I'm trying to explain it into a simple English that because of self-healing and other fault tolerance capabilities, Kubernetes is supposed to be highly available, right? Then obviously cloud advantages like multi-zone, multi-region, whatever, whatnot, they'll come. So advantages of cloud will come with Kubernetes. But if we are only talking about Kubernetes self-healing, like rolling updates, rollbacks, and then upgrades, right? Without downtime. So these kind of things are easily managed with Kubernetes. So I hope I'm able to simplify uh, introduction to today's session. What we would try to do is now pass on to Vidushi and Dipayan. They will take you to your journey of container and orchestration with Docker and Kubernetes. Ladies and gentlemen, happy learning. If you have any questions in between, feel free to stop us in between. But yeah, over to you, Vidushi and Dipayan.
All right. Thanks a lot, Rahul, for the introduction. Okay. I think my screen should be visible now.
Yes, we can
Is
see
it?
your screen, Vidushi. Yes.
Okay. It's lagging a bit. But anyways, so hi guys, welcome to the session. It's again a two-part session, which will be on container orchestration, container management. The first part of the session will be presented by me, and the second half, which is based on Kubernetes, will be presented by Dipan. Feel free to stop us in between if you have some questions or doubts. The agenda that we're going to discuss in this part of the session would be virtual machines and containers. What is Docker? How does Docker architecture look like? What are the containers? What are the images that contributes to a Docker? What are the ways in which, or the instructions that contributes to a Docker file? And finally, what is a Docker registry? You must be familiar with virtual machines, right? We had the concept of virtual machines since a very long time. What happened was in virtual machines, basically, they run on the emulating software. The emulating software can be any software that runs on your particular host machine. It could be a simple virtual box that you install, and inside the virtual box, you must be creating virtual machines based on the resource configurations that you would want to have your VM to get. So this is something which you were creating earlier. You were there was a hypervisor that sits between the hardware and the virtual machine. So the work of a hypervisor is to allocate all these resources that you pre-provide before creating a virtual machine. Whereas a container, it will just sit on the top of your physical server. It does not actually require a hypervisor, although it has its own set of components which manage the resources from the host, but not a hypervisor. So it's just an entity that sits in top of your physical server and in your host operating system. The container, the applications which are running in the container environment, they'll share a single kernel, which means, so right now, if you're working on the Ubuntu system, the kernel would be Linux, right? So they'll be sharing the same kernel, whereas VMs are like they're independent of kernel, so they have their own kernel creation. So you can run very easily, you can run a Linux-based operating system in a Windows-based environment or host, and vice versa. So a container, they're like very known for their lightweights and often are in MBs of size, just because they just contain the packages, the dependencies which are required to run the application. So you do not need to worry about the entire infrastructure that you were pre-configuring while setting up a virtual machine. Container are very lightweight. They just require those dependencies, those packages, which actually wants to uh, favor in the process of running an application and not the other ones. The size of virtual machine, it's quite high because whenever you create a virtual machine, you'll have to pre-configure the set of resources, whether it be a CPU resource, memory, or disk space. Right. So this is something which was a huge drawback in virtual machines, and some other drawbacks was like the startup time for virtual machines was very high. Usually it took about 15-20 minutes to spin up a virtual machine. And I'm not talking about configuring the resources. After configuration of resources, it took this much of time. Whereas container, they can be spun up even in milliseconds. So because of their lightweightedness and only containing the packages and dependencies that require an application, that are required by the application to run, this is the reason the startup time is very, very less, and because share the same kernel, and the processes that are involved with the spinning up of a container will actually take care of management of resources. So it's not necessary that a user needs to pre-configure what amount of resources a container should take in from the host system. It can consider these factors on its own. And obviously, if you want certain resources to be automatically be mapped to your container, then obviously you can have those resource configurations as well. But if you do not, then also it's fine to spin up the container. Right? So this is what is a primary difference between a container and a virtual machine. Coming to what is Docker, Docker is just a platform for shipping or packaging the applications. You might be familiar with the concept of packaging. If you're working with Java applications, what do? You create a jar or a WAR file, right? That is also a packaging of the application, right? So similarly, think of it this way: you have a jar ready already, right? Now, to run that particular jar file, what do you need? You need an environment. You need a host system that could run your jar file or a WAR file. So this environment and the dependencies that are required by the application all these contributes to the package which Docker creates within the container. So this is the environment that Docker provides to a pre-packaged or like a jar file, for example. The environment which contributes to running of that jar file is within the Docker container. So it eases the running of any jar file, any other packages, not just a Java application. Any application that you would create or think of can be provided with the environment by means of Docker. So it keeps them in isolated environment, which obviously means that let's say there are multiple applications or they're running as microservices, right? And one application is independent of the other application, which means it does not require communication between these two applications. So what it will do, Docker will create both these applications in a different set of isolated environments. So one application would not be bothered by or affected by the running of the other application. This is the level of isolation that Docker provides. You can significantly reduce the delay between writing codes and running it in production. Not just in production, in any environment, even for testing purposes, you can have any environment, and it's very easy to integrate your code and simply push your code to the centralized repository, whichever you are using. And if you integrate CI/CD with it, that would be much better. I hope you're familiar with the concepts of CI/CD. We have learned it yesterday. So if you have a pipeline, it would be very easy for you to integrate your code and create an image out of it. So it's very easy. The packaging of application is very easy. Running it in the environment is also very easy. So the isolation and security, this is something we already talked about. The containers are lightweight just because they only contain the required amount of packages and dependencies that an application requires. So we do not we do not need to rely on what is already installed in the host system. So for example, let's consider a server, and the server has nothing installed, right? And you want to run an application which needs a particular set of CLIs to be installed. Let's suppose, let's take an example of CI/CD only. Let's say your container needs to be running some CI/CD procedures, right? And it requires your CLI for any CI/CD tool that it is using. So that CI/CD tool, the CLI for it should not, it's not necessary to have it on your host system. A container will run in your host system in such a way that the CLI will be running on your container and not the host, and will be executing all the commands. For example, let's ease it out. Let's take an example of a Java application, right? So what do you require when you run a Java application? You require the environment, probably OpenJDK, that provide a runtime environment. So it needs not to be present in your host system where the container is running. It lies within the container. So if you have multiple containers that require different Java versions to be running, you can have it that way as well. So it's independent of what is installed in the host system. The next point is you can share those containers while you work. It's very easy to share the images. It's very easy to push them to Docker registries. It's very easy to pull them from Docker registries based on specific tags and commit hashes. So yeah, this is something which is doable. If you have a private Docker registry, we'll come to Docker registry later. Just consider this to be a centralized repository. Your source code exists in GitHub. So similarly, these Docker images are stored somewhere in the cloud. So by default, we obviously will use the public Docker registry, which is the Docker Hub. So you can easily share your images between multiple people in your team with the help of these centralized registries. Coming to the Docker architecture, we have multiple components actually. So this is the Docker client. It's just a command line interface, or CLI, that will allow the users to interact with the Docker daemon. Docker daemon, it's a background service, which is easily understandable by the word daemon. So this will run on the host operating system. It will provide the operations of image management, building of the image, and orchestration. Once this Docker daemon has these kind of functionalities imbibed in it, it will then pass it on the next set of instructions to containerd. Containerd is a container runtime, which is designed to like handle the low-level operations and management of the containers. And how it handles them is by means of runc and shim. Runc and shim, these are the two processes that runs in your host operating system. Runc will be like it's a very small and it's a very lightweight CLI wrapper for libcontainer. Libcontainer was what got replaced by LXC. Like LXC was the core component of Docker architecture before, but libcontainer then got involved with runc, and now runc is the actual component which is responsible for starting your containers or creating your containers, right? Then we have a component called shim. Shim is actually which implements daemonless containers. It's very interesting actually. So it's useful because it can decouple the running containers from daemon whenever a daemon requires an upgrade, so that your container does not, running container is not affected by the daemon upgrades. So this is what shim does. So you must be wondering how everything works when we create a Docker container, right? So we use Docker CLI commands. These are the Docker CLI commands that we typically use. We use Docker container run. We use Docker push, Docker build. So these CLI commands are passed by the Docker client. The work of a Docker client is to convert all the CLI commands into API payload and post them to the API endpoint. So API is implemented in Docker daemon. This Docker daemon will make a call to containerd via CRUD style API. CRUD style is create, read, update, and delete style API over gRPC, which is a remote procedural call. So it will make those certain calls to containerd. Containerd will then use runc to create containers, and containerd will create the image. It will convert the image to an OCI bundle. OCI is Open Container Initiatives. It's just a standard which is around the containers, which describes the format of the image, runtime of the image, and distribution. So once it packages into an OCI bundle, it will be required by runc. Runc will then interface with the kernel of your operating system, and it will pull together all the constructs which are necessary to create a container, which would be namespaces, C groups, etc. Right. So this is how a container is created. The container process is started as a child process of runc. So the work of a shim actually is just to keep the standard input and standard output streams open, so that whenever the daemon is restarted, the container does not terminate. So this is a very crucial component of a Docker. This is very crucial component of Docker, because earlier in the earlier versions of Docker, we did not have this component, and it was very hard for us to revive the containers that got deleted whenever a daemon got reloaded. So this is an improved version of Docker with the latest version. These many components will contribute to the microservice architecture of Docker. Right, because earlier we used to have monolith wherein we just had Docker, daemon, and LXC. LXC used to respond to the container request, and it used to talk to the kernel of the operating system. But now it broke down into several components, because these components won't be affected by anything that could disrupt the behavior of a Docker container. So this is the architecture of Docker. It's always like, it's sometimes people don't understand what is the difference between container and images, since these terms are very, like, they correlate with one another. An image is just a read-only template which will have all the Docker instructions that are required to create a container. And an image could be based on any other image. It could also be something which is created from scratch. So any additional customization is possible within the image. For example, let's say you take the base image to be of Ubuntu, which says that Ubuntu will be your base operating system on which the further execution will take place. So if you want to install any web server, Apache, Nginx, anything, the next instruction would have these installation steps, so that the image is constituted of all the instructions that is written in your Docker file. So it will create a layer for each instruction, and those layers are built again and again if there is any change. So this is the part of Docker which makes the image so lightweight, small, and fast when we compare it to other virtualization technologies. Whereas a container, it's a runnable instance of an image. Image is something that you can easily push to a registry. You can easily pull from a registry. So this is a kind of a package of the instructions that lie within your Docker file. You can easily copy it from one location to another location. You can send it, you can share it with your team. So this is image, and the container is actually the instance which is running that image. So you can create, you can start, stop, move, or delete a container using Docker API or Docker CLI, and you can connect to a container you can connect to a container, and you can connect a container to one or more networks and attach storage to it, and do all sort of manipulations that you would want your container to perform, like your application to perform actually. So a container is defined by its image as well as any configurations option you provide. Configuration options could be attaching a volume or attaching a network related component. Let's say if you want to have a network separated for your front end and back end applications, you can also attach those kind of configuration options to your container when you start it. So when a container is removed, any changes to its state that are not stored in persistent storage, they will disappear for obvious reasons, because it's considered, the storage is considered to be ephemeral, which means once a container is deleted, all the files that lie within the container that you might have created during the container execution, they will be also deleted. So this is what container and images are. Then we have Dockerfile instructions. Whenever we want to create an image, obviously we'd be having a Dockerfile. Dockerfile would be containing all the instructions that are required to create an image. These are some of these instructions, but there are other instructions as well that you might want to use. But if you see a generic Dockerfile in your project, then you should be familiar with these kind of Dockerfile instructions. The first instruction is a from instruction. This will set the base image for your Docker container, and all the execution steps, all the things or commands that needs to be installed will lie after this from instruction command. So this will be acting as your base image or base layer. Work dir will set your working directory, which means by default, if you don't set your work dir, everything, if you exec into a container, it will be on root. It will be mounted to root. So work dir is to set up your working directory wherein you would want to copy your source code. Labels are again something that you would want to provide to hold the metadata information. For example, if you have to create multiple Docker images, some images could correspond to your front-end application, some images could correspond to your back-end application. So you might want to add labels to both of these entities, so both of these front-end applications and back-end applications, to know that which container would contribute to which set of application, so that you have, let's say, all the applications with the label set to front end, they should be mapped to a single network, and all the Docker applications which are mapped to a label called backend should be mapped within a different Docker network. So this is where you can use labels. We have copy instruction. Copy instruction will copy the data from your host machine to a Docker registry, sorry, not Docker registry, Docker container. Add instruction will work similar to what copy instruction does, but it can also extract the zip files, star files, and it can also copy something from the remote URLs to your Docker container. env is, it's very common. It's just that if you want to have environment variable configured to your Docker image, you can have env instruction. Run instruction is very important. So it will execute all the commands that you provide within the run instruction. So for example, if you want to perform update, okay, this can be done in a run instruction. If you want to install any binary, any CLI, this could be also embedded in a run instruction. The next is CMD. CMD is just like, if you want to execute something, if you want to display something, similar to what you do in a general when you have a shell open. So all these kind of instructions can be imbibed in CMD. Entry point is like, it's similar to CMD, but it's just that if you want to make a container executable, you can provide a command for that container to run, and CMD and entry point can work together, as an entry point can hold the command and CMD can provide additional parameters to the command for it to run. We'll see more of it in the demo, so this should be clear then. But yeah, these are the Dockerfile instructions that you must be familiar with. Then we have Docker registry. As I mentioned before, it's just a service that allows user to store and distribute the Docker images. For example, if you're working on a team and if you're working on a project, you created a Docker image for your application, and now you want it to send to a registry for some other team to pull and execute a container in their machines, or even run it in a production dev QA testing environment. So this is the way you would do it. You'll create an image, you'll push it to the Docker registry. Some other team will pull the same image from that Docker registry with the same image name and tag, and they'll execute that in their either their host machines or in any other environment they prefer. So there are two primary types of Docker registries. One is Docker Hub. This is very common because it's a default public registry, which is provided by Docker, and it has a collection of publicly available Docker images. Some are verified by the publishers, and it's always recommended to use the Docker images which are verified. And we can also use a host or host our own private Docker registry if we do not wish to make our Docker image public, or if we do not wish to store it in internet, so we can always store it in our local by means of private Docker registries. And we can also have them hosted on-prem or on cloud platforms like AWS, GCP, or Microsoft Azure. So this is also a way of doing it by using their managed services of the cloud. We can also integrate it with their Docker registries. So now we'll look at how we'll create a Docker file, how we'll create an image out of a Docker file, and how we'll run a container. But before we move to demo, I just want to keep a window open for any questions. If somebody has any questions up till now, please feel free to ask. Okay, I see I've already taken half an hour. But anyways, if you don't have any questions right now, I'm sure you might have something you would want to ask. So please ping me after this session as well. I'd be happy to answer. We'll just quickly move over to the demo because I took most of the time. Let's start by creating a Docker file, a very basic Docker file. So as I mentioned, the first instruction that you write in a Docker file is a from instruction. From instruction is used to set the base image. So right now we'll see all how the instructions work in detail. So I'm running one instruction at a time. So this would help you understand what each instruction is doing, right? So right now my Docker file only has one instruction, which is from, and it's taking the base image to be Ubuntu. I'm going to save this file and I'm going to build this image. Let me tag it with the name demo, and the build context is set to dot, which is the current working present working directory. So it created the image out of it. It pulled the image from the Docker registry. The image was Ubuntu and the tag was latest. If I haven't provided any tag, it will be automatically tagged with the latest tag. I will then, so if I do Docker images, now this image is already present, as you can see. And if I do Docker run, and I want to remove when this container exits, I want to have an interactive session with this image or the container. I will type in the name of the container. Let me type in demo container, and the image that I would want the container to take is demo. So once I do that, it will take me to the container since I've added an interactive session with it, right? So when I do an ls, how it should look like, it will look like a typical Ubuntu-based host. So it will have all the files, or the directory structure will look exactly as it would look in your particular host, in your particular system. If you have, obviously, if you have Ubuntu in your system, right? So it will have all the binaries, it will have the boot folder, dev, and all the folders that you would want to have in the Ubuntu-based system or localhost. So this is something which is there if you only run a vanilla Docker container with just a single instruction, which is just executing the base images Ubuntu. We have other instructions as well. We have work BIR instruction. which sets your working directory. So it's also like if you build this image now, let me tag it with v1 version. And it's always recommended to change the tag so that you have version control, and you can go back to the previous image, and you do not disrupt the previous running image, which was stable. So now if I do docker run hyphen it hyphen name any container, and my image with the v1 tag, if you see the present working directory changed to app. So this is what happens if you provide a work directory. If I exit this and I run another instruction, which is copy, I want to copy everything from my present working directory to the app directory of a container. And let me also touch a file here. Right now, if you see, my present working directory has two files. One is file and the other is Docker file. I want to copy these two files in the app directory. So also very important thing, copy is the instruction that you would want to use to copy your source code to your Docker container, right? So you wouldn't want to copy the Docker file there because it's of no use, and it's just creating an additional file in your source code directory. So we have another file called .docker ignore, wherein you can specify the files that you want Docker to ignore during execution of your build. So I'm going to type Docker file here. And now when I build this image with, let's say, a v2 tag, and if I do docker run, init 2, and the image is version 2, and you'd see, okay, so this is something which got copied to my Docker file, and it executed. So it took asterisk, so it will copy everything. My build x starship.toml. This was something which was present in my present working directory. So it included all those things, and it contributed it in a single app directory, which I specified in the work directory section. The other commands are, give me a minute. So the other commands would work in a similar fashion. I have the add command. Add command is like, it's very much similar to your copy instruction. It's just that if you want to copy something from your remote URL, you'd be able to do that. And if you want to untar, the default behavior is to untar the files which are zipped or tarred. So it will do that as well. A very common instruction that you might see in a Docker file is a run instruction. So for example, let's see how run works. So if you want to do an update, we get update in your Docker container, and probably you would also want to install anything. Like let's say if you want to install tree command, which is very common, and by default it does not have tree installed. So if you want to install any CLI, if you want to install Nginx web server, if you want to install Docker CLI, you can always add these sort of commands in the run instruction. And if I build this again with demo new tag, okay, I think I mistyped. It's not taking an apt instruction for some reason. But anyways, if you want to have it, if you want to install any CLI, you would be able to do it this way as well. Let me try it one last time. I'll probably do one instruction at a time. Okay, so this time it's only performing one instruction, which is apd get update. It is right now updating your Ubuntu libraries and binaries to the latest version. But if you want to install anything apart from just updating it, you can always add multiple run instructions. But the best way to do it is via using it or typing all the instructions in a single or in yeah, using a single run instruction in multi-line instruction for that. So if you want to have it this way, you can use apd install tree. Probably this should work. I am image v1. Oh, it's not resolving this for some reason. I need to check this, but yeah, all the instructions that you would want to have in your Docker run command, you can have it here. The other important command that you might want to use just to make your container executable is your entry point instruction. So entry point instruction will take in all the instructions that you would want your Docker container to run when it runs. So it should execute something. If you want that to happen, you can have the entry point instruction. So I want my Docker container to run the command called echo. And CMD, as I said, it works in coordinates with entry point command. So CMD will provide default parameter to what entry point is doing. So entry point is trying to echo something. CMD could act as a parameter for it. So let me just echo hello. And let me build this command. Entry point. Okay, and if I run this container now, and the image was entry, it's going to print hello. And one feature that comes along with CMD is we can override the CMD parameters during the execution of a Docker CLI. So if I type anything hello world here, so it will override the instruction from CMD and it will now echo hello world. So entry point is making the container executable and CMD is just providing a default value. If you override it via the Docker CLI, it's going to override everything that we provide as an additional argument to this run. So this is how it is working. But if I talk about the real use case of entry point, like what you would want to do with your entry point or how your Docker file would look like, what you would do is you will create a working directory, and let's say it will have your source code. You'll actually copy your source code from your local to src folder, and let's say this source code you had a jar file that you might want to run. So now your entry point instruction would look similar to this. You'll have um, Java, and you will provide what it needs to do, which is java-jar a tag, and then you'll provide the name of your jar file, which could be app.jar or whatever the .jar. So this entry point will actually execute your jar file, and the container by default will have something to run. So the default behavior of a Docker container is to execute the command that is specified during the container startup, and it will exit once the command is completed. So if you haven't provided any command, the container will keep if you haven't provided any command, the container will stop running and it will exit immediately as soon as you start it. So the container is active only when we have either we have an interactive session with it, or we provide something for the container to run until unless we explicitly stops it or delete the container. So once you do that, this is how your Docker file on the very basics. Like this is something which will definitely be present. Apart from this, there are so many other instructions that you might want to use. For example, env or a run instruction that you would use to install anything like OpenJDK, or if you want to have a much lightweight image, go with distroless images. Like you can just type OpenJDK here, and you can define the version of OpenJDK, which I think the latest, or at least few versions back is 11. So you can provide distroless image, which would be OpenJDK 11, and you can just copy your source code here, and you can run java-jar app.jar. So this would make your container executable. This would make your container run that particular jar file. So this is how it goes, and this is how Docker works. Apart from that, we have multiple other scenarios wherein you can integrate it with user-defined networks. We have multiple networks in Docker. We have the default bridge network. We have overlay networks when we work on multiple Docker hosts. And it's basically, if you have to work with multiple containers, it's recommended you use an orchestration tool, which we are going to discuss further, Kubernetes. So if you want to have a brief about what is Docker, this was it. And if you wish to know more about how we can have volumes attached to Docker containers, how we can have networks, different set of networks for different containers, this is a very short time duration for it. And we're already 15 minutes late. So I'm going to stop sharing and I'm going to pass the screen to Dipan. Before that, do you have any questions from Docker? Okay, Dipan, over to you. And still, if you have any questions, please ping me after this session.
Yeah, thank you, Vidushi. I'll share my screen now. Yeah, I hope my screen is visible. Let me go to the slideshow. Okay. So now we'll look at what orchestration is and how it is achieved using Kubernetes. So till now you have learned what a Docker container is and how these are launched, right? But now we'll understand what this orchestration is and why do we need that. So the agenda will be Kubernetes, what is that and why we need it, its architecture, managing configuration and secrets in Kubernetes, some networking in Kubernetes, some advanced features, and we'll deploy our demo application in Kubernetes. So before we jump into Kubernetes, let's understand why we need Kubernetes or why we need orchestration. So first, let's understand what orchestration is. Let's say we have a application. We want to create an application and it is very simple. It has a front end and a back end. We create two Docker containers, we run them, and after a few months we think that no, we need to add some more services like some authentication, authorization, some databases. So we start increasing the number of Docker containers, and now there are 10 services and 10 Docker containers. Now what happens, the application popularity increases, and from 10 users we now have 10,000 users, and so we need to have more number of Docker containers, right? So these 10 Docker containers will not work, so we need scaling for them. So when the users are very high number, we want the number of containers to grow from 10 to 100, and when it is less, we need to reduce that to 10 again. So these things are very difficult to control when we use the Docker CLI. Docker is very good at creating these containers, building the images and creating the containers, but it somehow lacks the capability to manage all these multiple containers. So this is what Kubernetes solves. This is what orchestration is. So Kubernetes actually provides us a platform, abstraction over these Docker containers so that we can manage multiple number of Docker containers very easily using a CLI or maybe a GUI, anything we prefer. So what Kubernetes does is it's an open source system for automating the deployments of these containers, for scaling them, and for managing of these applications. It adds a layer of abstraction and simplifies managing of multiple Docker containers, their configuration, and underlying network configurations. So one of the challenges with a multiple number of Docker containers is we'll have to manage the configurations. Let's say we have our application in cluster mode, and every application should have a different configuration. So if we run it using Docker CLI, it's 10 times running the Docker command. And if we somehow automate using script, we'll have to keep in mind the how the configuration changes will be implemented in all of the containers. So that is something Kubernetes manages very well. It also adds an extra layer of isolation on these containers using Kubernetes native namespaces. So what namespaces are? So let's say we have an application and we want to run multiple instances of it, right? So what Kubernetes does, it has a concept called namespace, and we can run these applications in a namespace. So when we have different namespaces, they are logically isolated from each other. So if we run instance of application in different namespaces, by default they will not be able to interact, like they will not be able to discover each other. They will be logically isolated. We can have network connectivity between them. That is also a possibility, that is also an option in case if anyone needs it, but namespace is a way to have a logical isolation between these applications. We can launch multiple instances of them and still have a isolation between them. And Kubernetes is continuously growing as we speak. It's actively developed and it's actively released every month, every 2 months, right? So it now till now till this point, Kubernetes also integrates very well with open source applications as well as enterprise self-hosted or SaaS applications for monitoring and security, like Datadog, like New Relic, everything. Like most of the applications now, most of the enterprise applications have Kubernetes native deployments for Kubernetes monitoring, security, and etc. And one of the benefits of Kubernetes are it includes scalability. We can automate the deployment, and we can use based on the usage we can scale out applications. And but one of the drawback of Kubernetes is it is really difficult to set up and manage. So that's why most of the cloud platforms like AWS, Azure, GCP, DigitalOcean, they all provide a managed Kubernetes. So what they will do, they will manage the Kubernetes for you. The only will have to use that, because managing and setting up Kubernetes is a very difficult thing, because it has so many moving parts and it will be very difficult to manage. So that's why these cloud platforms provide a managed solution which is not that costly and can be used for our application. So let's look at the Kubernetes architecture. So Kubernetes has a master slave architecture. So it's like the traditional master slave, only the masters manages the slaves and does all the logic of how these containers will be scheduled and all. So if we look at the master, so we'll not go in depth into all the components, because that will be really confusing for you, since this is a very beginner session. So but at a high level, we have Kube Scheduler, HCD, Kube API Server, and the Controller Manager. So this HCD is a database. So Kubernetes, the configurations, the containers we deploy, Kubernetes will need to store these information somewhere, right, and persist it. So that's why HCD is used. It's a key value pair database where these informations are stored. The scheduler and controller managers purpose is to, like we want to schedule an application, right? We want to schedule a container, we want to scale it, we want to see that if we set the replicas to be 10, we need to Kubernetes need to ensure that at every time our 10 instances containers are running, right? These things are taken care by scheduler and controller manager. And what API server is, it's the entry point to the Kubernetes master. So any commands we run, uh, anything we pass on to the Kubernetes master to get to be deployed, it goes through the API server. So API server is kind of in the center, and every other components interacts with it to get all the information. So there is also one other thing that's called Cloud Controller Manager. So as I said, Kubernetes most of the cloud services provide a managed Kubernetes service, right? So for that, these Kubernetes should have a pluggable architecture, so that every cloud can like develop their like cloud centric application and plug it into the Kubernetes and somehow be able to manage this Kubernetes cluster, right? So that's where Cloud Controller Manager comes into picture. So every cloud has their like self-developed controller, and they connect it with the Kubernetes, and hence they are able to control the Kubernetes cluster. And now when we look at the agents, there is a kubelet, kube proxy, and a container runtime. So what kubelet does, if kubelet is mostly responsible for running all these containers. So as we looked at the Docker architecture, right? We have Docker, we have Shim, we have Run C, right? So we have container D. So what Kubelet does, Kubelet gets the all the information from Kube API server, and it actually instructs the container runtime to run these containers, right? And once the container dies, it's Kubelet's like responsibility to again instruct the uh, Docker container runtime to run it again. And what kubeproxy does is kubeproxy basically manages the networking level at the agent. So let's say we have multiple containers running on multiple nodes. So there needs to be there should be a networking between these containers so that they are accessible to each other. That's done by kubeproxy. Kubeproxy actually abstracts this and creates a overlay network so that these containers are accessible from each other. So now let's look at what some of the features of Kubernetes are. So in Kubernetes, firstly, there is something called pods. So in Docker, there are containers, right? So these containers are managed by Docker. But for Kubernetes, Kubernetes adds an extra layer of abstraction above these containers, and they're called as pods. So Kubernetes actually manages these pods, and these pods are actually containers and nothing else. But using these pods, Kubernetes is like very easily manages these containers. So when we talk about pods, it's under the hood containers only, one or multiple containers. So pod is basically a container with some extra features and extra functionalities. So replica set, so in Kubernetes, let's say we want to run 5 containers, and we always want to ensure that these 5 containers are running no matter what. One goes down, one should come up, right? It's called self-healing. So we always want to run 5 containers. So that is done using replica sets. So replica sets is basically a layer above pods, which ensures that these number of pods are always running. And what deployments are? Deployments are another layer above the replica set. So deployments in turn manages these replica sets, and these replica sets actually manages the pods. So it's kind of like a tree. We have pods at the lower level, and then the replica sets, and then the deployments. So when we create a deployment, it under the hood creates a replica set, and these replica sets control the pods. Now, one question you might have, that why do we need replica set then? Or why do we need deployments? Because we have pods and we can control these pods using replica sets, right? Why do we need deployments? Okay, so one of its use is like Kubernetes have a feature so that we can roll back to a previous configuration, previous deployment model anytime. So how does Kubernetes manages that? So let's say we have a container image, let's say with version 1. So what when we create a deployment for it, what it will do, it will create a replica set which will create a pods of image of version v1. Now when we change this image to v2, what deployment will not update that replica set. What deployment will do, it will create another replica set with the pods of image version v2. So now what happens if we roll back the deployment to the previous version? What it will do, it will scale down the newer replica set and scale up the previous replica set with the older image. So at a point of time in the cluster, we have all the versions available. So that is what deployment provides, like the extra functionality over replica set. It manages these replica sets where each replica set points to a different configuration, and we can switch between these at any point of time. So Kubernetes also has a feature through which we can manage the configuration and secrets. When we talk about microservices, for one service to talk to another, they should have some configurations which are specific to application. They should have some secrets like for connecting to the database or something else, right? So Kubernetes has config maps and secrets to manage these configurations and secrets. So config maps are basically key value pair uh, configurations where key is a name of the property and value is the value of the property. We can also have a file itself as the config map, like the key will be name of the file and the value will be content of the file. That is also possible. And in secrets are similar to config map, only the difference is the value in config map is a plain text, and in secrets it's a base 64 encoded, and it is stored in that way in the Kubernetes. So the like the advantage of this is at any point of time, if anyone looks at these secrets, they will not be easily able to decode it. They'll have to decode it on a base 60 using base 64. So that's a minimum level of security that's been added to like to keep these secret values as secret and not expose it, right? But as I said, Kubernetes has a pluggable architecture, so we can like add third party secret management tools. With Kubernetes we can integrate like Azure Key Vault, the AWS secret manager, everything with this Kubernetes to keep these secrets stored uh, in a more encrypted and more secure way. So now let's look at Kubernetes networking. So we have deployed the applications as pods and deployments, and we have created custom configurations for them. But how do we access it from outside? So if I give you a high level overview, so Kubernetes, when we deploy a Kubernetes, there are multiple networks that are created. One network is where these agents and masters are created, and there will be another network inside uh, these agents. It can be called as a network namespace, so where these pods will actually run. So now we have these pods running inside that network namespace, which is not accessible from outside. So there should be a way to access these, right? So this is done by a Kubernetes resource called services. It's a method for exposing the applications running inside as pods to outside network, or maybe from outside other pods. So a key aim of service is we don't need to modify our existing application to use unfamiliar service discovery mechanism. We can run code in pods, and whether this is code designed for cloud native world or older app, we use service to make these pods available on network. So basically what it is saying, we run the application as pods. We do not need to like think on the application level that how these will be exposed. Using service, this is very easily obtainable. We write a simple YAML config and they will be exposed outside. So there are actually three types of services. One is clustered IP. So let's say we have three namespaces, so A, B, C. We have some applications running in A, and we want these applications to be accessible from the namespace B. So for that, we create a cluster IP service. These cluster IP services are only internally accessible inside Kubernetes, and they will not be accessible outside. So the applications running in namespace A will be accessible from applications running in namespace B when you use the cluster IP service. So and there is also another type called node port service. These node port services are mainly used to like expose the application to outside world. So what happens, let's say we have an application running as a pod. So in node port service, what happens, these applications are like mapped to a port ranging between 30,000 and 32767 on one of the nodes. So let's say I have a node with IP 10.1.1.1, right? And I create a node port service of an application running on that node. So that applications, well, let's say that application runs on port 80, right? That port 80 will map to a, let's say, port 30,000 on that node. So if I take the IP of that node and port of that node, port, let's say 30,000. So when we dial that on the browser, we see that like we'll be able to access the application, right? That's what node port is. And the last part is load balancer. So there is a drawback of the node port. It's that the node the node on which these are running, right, these applications are running, the ports are getting exposed outside, and that is a very insecure way, because hackers can find a way into the node and into the running workloads using this IP. And second drawback is that everyone will have to remember all these arbitrary port numbers ranging from 30,000 and 32767, right? So that's why load balancer comes into picture. So what load balancer does is it creates a load balancer instance. A load balancer is, let's say, a load balancer is specifically a VM running some application, and which what it does, it receives a request on a port, and then it distributes them into the backstream applications which are running as the targets. So this is what load balancer service is. It will expose the IP and some ports, let's say 8443, it can be any ports, and any request that is being received on that port, it will route it to the backend application. And there is also another thing called ingress. So ingress is a bit advanced, but still I'll give a basic overview on that. So ingress basically uses these load balancer services and a resource called ingress. So what it does, it uses a reverse proxy application called ingress controller, and based on rules called ingress, it evaluates the routes, the domains, and using these rules, it will route every request to the application that is configured.
I think मैं थोड़ा सा ना simple English में समझा देते हैं. If you go back, networking थोड़ा सा ना simple English में समझा देते हैं. What happens, guys, specifically in terms of when you're trying to access your applications over the internet or over a particular network. Obviously, a node port ranges is from 30,000 to 32767, right? So when you're trying to expose a service, how do you make sure it is accessible? So a service is defined with the type set to node port. Okay. Now Kubernetes by itself assign a random high port number from 30,000 to 32767. Okay, to the service. Now each node in the cluster opens the assigned node port to its network interface. Right. Now the traffic sent to this node port on any of the IP address that is forwarded to whatever service or ports within the cluster, right? Every port is a service in itself, right? So when you want to expose a particular service to external clients or to anything external to your cluster for testing or dev or internet or whatever, now you are exposing a service via node port. You are making this accessible from any IP address. Obviously, the security comes into place. But to access a service exposed service, you will access it via this node IP and node port, right? Right. Simple networking definition. So, along with cluster IP, load balancer, and node port, these are the things required, or you have to mention them. And specific each service obviously has a different particular use case depending on your requirement. But exposing it to any extra, because it is a service, right? End of the day, so you're trying to access a service, and in our language we'll call a principal will have an access to a particular service only. So this is called ABAC, access based role, right? And how do we control it? We control it via this, because in ingress means incoming traffic, in egress means outgoing traffic. And how do we control the traffic is via node portal, right? So we'll block certain ports for particular uses, right? Go on, Dipan.
So Rahul, just one question. Okay, let's say I have deployed some of my APIs. Okay. Now the first thing is it will be physically available on some port, right? And to access it, we will have one, let's say, a cluster that is kind of a server, is it?
Go on, what is
this is over. Okay. Say, let's say I have deployed one of my API. I want to access it outside world, right? So finally, there'll be one load balancer. Whenever I'll be hitting some API, it will go to the load balancer, and load balancer will find the particular cluster which can serve this service, right? Is it?
So you want to access the internet, and you are asking
internet. Yeah.
whether, and you are asking, your question is whether you need everything, load balancer, node port, or egress.
Yes.
Interesting question. You don't need everything. You can always have a egress and node port assigned. Maybe you don't need a load balancer at all.
Okay, so node port is just a configuration mapping your local port to the
We call
global
it a
port.
service. We call it a service. So
Yeah.
everything is a service, right? So I mean, by the definition, everything is a service. So
Yeah, but
if you
what
are
I'm trying to say is node port is just assigning some, let's say, global port to that service, comparing to some local port available, right? Where the service is deployed, right?
okay, node port is a service. Its
Mhm.
type set is node port.
Mhm.
By default, yes, obviously it is used, whatever you're saying.
Mhm.
So any traffic sent to the node port on
Mhm.
any of the node's IP address, you can
Mhm.
forward it to whatever place you want, right? Now you can
Mhm.
forward it to your respective service ports within the cluster, right?
Yeah.
Now, if you are trying to expose it to external
Yes.
clients or
Mhm.
outside the cluster, for example, a different environment or a Windows environment or a Linux environment or from the internet, it you are making it accessible from any IP address as long as you have a port, right? And
Yeah.
how do we do it? IP colon port.
No,
That's it.
yeah. Yes.
That's it. So we call it as service. So everything is a service, and the type set is defined. For example, cluster IP, load balancer, node port, external name, egress. Everything is a service, right?
Yeah.
But
But
if your
see,
question is,
the next question is, Rahul, let's say we are mapping some port, internal port to the external port, but
Hmm,
is this mandatory? Like, what's the benefit of doing this? Like,
uh,
let's say if I my API is deployed and it is running on 8080 port, right? Is it
okay.
mandatory to map it to 30,000, let's say? And let's say if I don't map it, I don't want to
If
map
we
it.
are using node port,
Mhm.
then obviously you will go there. But if you are not using node port, you are only using egress and load balancer.
Mhm.
Sometimes what happens is we forget to give node port. Then how do we do a workaround? That is a workaround, you are saying.
Mhm.
Right, Deepa? I think we did it in uh, one of the, I think, okay, it was in one of the assignments wherein my question was not use node port, but we can use load balancer and egress. Because what happens is, you remember, if we have to access to the internet, we can only use proxy and that's it. What is it? It is just a link. And what is the link? Link is just a IP and a node, right?
Yeah.
So
It,
you are trying to make a service use. How do you access it? You are trying whatever port you want. You are trying to make sure your service has a set of ports available who are going to a set of ports, right? By default, you have the smaller ports are already defined for particular services. Load balancer then thinks of assigning a bigger port. But your question is it is necessary? No, it is not necessary to use every service. You
Mhm.
can use load balancer and you can do without load balancer if that is your question. Because when it comes to load balancer, you're trying to ask for money or the service charges. Yes, we can avoid load balancer. But when I am trying to avoid load balancer, I'll probably have to make changes in my configuration every now and then.
But I believe load balancer could be kind of a mandatory in terms of, let's say, multiple instances which are serving this request. But let's say if we can cut down
That we
on
are
this.
talking about by default ALB, right?
Mhm.
Now I'm talking about network load balancer. Now network load balancer has their configuration dependent on this, right?
Yeah.
Whereas application load balancer is on a traffic, right?
Yeah.
Now network load balancer, uh, how do you define network load balancer? So
No,
network
see,
load
let's say
balancer.
within, let's say we stick to within this Kubernetes, we have a load balancer, right? There
Hmm.
might be different ports, and based on, let's say, the
Based on
availability of.
that, it will go to different ports within
Yes,
a cluster.
yes.
Your distribution is different ports, so that workload. So how do you what makes the logic?
What? So sorry, I didn't
So
get you.
so how
What?
how how the traffic is moved? The the traffic is routed to individual ports
Ports.
associated with your service.
Yes.
How do you do it? The network load balancer listens to what?
Request.
The network load balancer listens to IP and port. Understand, right? The network load balancer will always listen to your IP and port. Then it will say, okay, I am, because when you're writing logic that my API to provision a network load balancer, how you are doing it? You're telling it, you are defining the logic as move this, move that, depending on your IP and port. For example, I'll give you a very good example now. There are two type of messages which comes via types. UDP and TCP, right? These are the requests, right? 443 and one more. Now, you say UDP messages are important to me. TCP messages are not important because they contain everything from login, logout, what a person is doing. But I only need UDP messages because it tells me the event type, right? Now, how? Because I'm talking about log aggregation of it. Now you will say, I have millions of logs. I only need UDP. Can I differentiate? Yes. You'll go into the config file. You will now differentiate. Your logic is dependent on what? Port.
Okay.
Right. So you're blocking a traffic log aggregation. You're doing only for UDP because you are able to map the port and say, okay, I'm blocking this traffic on this port. I don't need it. Port is necessary. I mean, not mandatory, but necessary for you to do these kind of operation. If you don't have to do this kind of operation, you don't need it. You don't even know by default what it is assigning, so you probably won't care. But um, um, what we do, we specifically take care of it because we might end up in cases where there is no load balancer, and then we have to take care with node port and ingress and egress rules. So what we do is we usually play around with proxy. HA proxy is one of the load balancers, not kind of a load balancer or a security load balancer like F5.
Yeah,
Right?
see, Rahul, those could be advanced level. What I was thinking is, let's say if we have a simple application, right?
You don't need
And
a
if we don't need this, right? Because there'll be
right.
multiple, let's say, call here and there going, and it would add some, let's say, time latency, right? It would
Yes,
definitely
latency
impact, let's say,
latency
response.
usually happens in transformation. If your transformation is quick, latency will not happen because lambdas and functions don't really create latency unless there are millions of requests or the bus is having a lot of messages. Latency usually happens within functions, outside functions. So, but if you're even this load balancer will not increase latency, but it will only increase latency if the transformation is big. And we don't really do transformation here. We do transformation at a later stage in life, right? On in the workflow. But yeah, you can avoid having load balancer. You'll probably have HA proxy. You'll probably have
Yeah,
ingress and not port and event.
yeah. Go ahead, guys. Sorry.
Okay. Thank you. Very good question. Thanks a lot, Neeraj. These are
Yeah.
practical use cases. Go ahead,
Like
Dipan.
I would like to one more add thing, Neeraj. So the thing you said, right? So yeah, let's say you have multiple applications, you have multiple load balancers, right? For them with port exposed. Let's say you have three applications all running on 8080. So node port is an option, but the problem is you will have arbitrary ports, right? So you can have three load balancers, but now the problem will be three load balancers means more cost, right? So to like have a solution for these, right? Have lower cost, but have a generic solution, a simpler solution. We have Ingress. So in a simpler term, we can say a Ingress is basically a API gateway and nothing else. So we map a domain. You said there are three APIs, right? So through Ingress, what we can do, we can have three API paths. Let's say /API1, /API2, and /API3. And using this paths, we can access those APIs. That is also a viable solution and a better solution than load balancer. So
yeah. I mean, there's multiple use cases, but this is one of the good use case that you bring up.
Yes.
Thank you.
Yeah.
Cool, guys.
Okay. So going forward, these are some advanced features. I will not go through them now, but I'll give a uh, like overview of all these because these are really important but are little advanced. So what is stateful sets? So stateful sets, by the name, it is to deploy and manage stateful applications. So let's first look at what challenges of stateful applications are. So let's say we have a database, and why databases are stateful applications? Because all of the instances will have a set of data with them, and these data are necessary, so it is a stateful application. So we have, let's say, two nodes, one is master, one is slave, and they both have some conflicting data. And so when these pods go down, they need to come up exactly as they are. These, their host name, their configuration, uh, these don't needs to be changed. These should have be completely identical, and every such application or container should have their separate storage so that they can store their data separately and they should not get mixed up, right? Deployments do not address that. When we create a deployment, once a pod goes down, a pod will come up with random names with other things changed, and all the pods running under a deployment will share the same storage. But that's not something what we want when we want to run a deployment stateful application, right? A database. So that's what stateful set does. It creates pods, and each pod will have a fixed identity, and these will not change even if the pod goes down and comes up, and each of the pod will have a separate volumes. Now next we go to daemon sets. So let's say there are 10 nodes, 10 agents running, and we want some pods to run on all of these nodes, right? No matter what, exactly one pod running on all of these nodes. So what can be use cases of these? Let's say we want to monitor each of the node. What are the matrices? What is the memory? What is the CPU? Or we want to gather some OS or kernel level logs running for each of the nodes. Or we want to get the application logs for the containers running on these nodes. So we need to have some daemon processes running on all of these nodes, right? So one other way is to run our application directly into these nodes and get the matrices. But when we go into, let's say, like cloud managed Kubernetes, right? We do not have direct access to these nodes. We can only use it. In that case, these daemon sets come into picture. They run exactly one pod into all of these nodes, and these pods can get all the works done that we could have got it done using the native services, native application directly running on the VM. So daemon sets basically means daemon services uh, running in each of the node. So daemon sets are used to like run these daemon applications, exactly one application on each node. So that's what daemon sets do. And volumes. So we have containers running. Now these containers will need to store their data, right? So we need a persistent storage so that these data are persisted and it does not get deleted every time a container comes up. By default, the containers are designed in that way that once a container goes down and comes up, all the data will be lost. But what if we want to store these data? Let's say in stateful set, we have databases, right? We want these data to be persisted and not deleted every time it restarts, right? So that's where volumes comes in. Volumes, or in Kubernetes term, they are called persistent volumes. So what these do in persistent volumes, the data is stored in a disk, in a file storage, in a host path. There are many plugins that plugs into different storage options, but uh, at a high level, volumes are used to persist this data. And what are jobs? So let's say for some reason, for every day at morning 7 p.m., right? I want the Docker images to be cleaned up, the stale Docker images, the stale containers to be cleaned up every now and then. Let's say every day at 7 p.m., right? So I need some application, some job that will run every day at this point of time, right? So that's where jobs come in. There are there is a simple job and there is a cron job. The jobs are simply we run the task once and we are done with it. And cron job means it runs in a cron schedule, like every day, every minute, every month. So it is based on the cron schedule. And when this cron schedule will match, it will the job, the application pod will run and will do its duty, and then it will be killed. And then again at the next schedule, this will run. So these are some of the advanced features. Now let's go on to the hands-on. We'll deploy a application on Kubernetes. So we'll deploy to deploy an application, we'll need to write a deployment config in YAML. And now we have written the configuration, right? But how are we going to apply it to the Kubernetes? So for that, Kubernetes has a CLI called kubectl. We'll use these to apply these manifests, and then also we'll create some custom configurations for our applications. We'll create a service so that this application is exposed outside. So let's go to the demo. So this is a very simple demo, but it somehow resembles how our application is configured. But for it to be easy, I took a simple Nginx container, and the Nginx container will just print a line and it will print an image and nothing else. So let's look at the deployment configuration. So this is the part where I give the kind, if it is a deployment, if it is a pod, if it is a service. And this is the API version. So as I said, every interaction to deploy application or anything is done with the Kube API server, right? So Kube API server has the list of all the APIs and what API points to what type of resource. So this is the API group or the API version that denotes like what type of application, like in which API group this deployment exists. So this is the API version, this is the kind, and I give it a random name. It can be anything. I set the number of replicas to be 1. And now comes one of the most important part. So there can be 10 deployments, and each deployment can have multiple pods. So how will each deployment know that which pods they are supposed to manage, right? So that's why there are labels. So we label each pod with some unique label and identifier, and the deployments, what it will do, it will look at these labels and it will match the every pods which has label saying app is training demo deploy, right? So this is the role of the selector. It will select the pods that it needs to manage. Then we have the template part. Template part is the most important part where we give the configuration of the pod, right? This is the part configuration of the deployment, and inside the deployment we give the configuration of the pods. So here in the configuration of the pod, we label the pod with app training demo deploy, exactly same as this. So here we label the pod with this, and here in the deployment, we say that select all the pods which have this label. So these and these should always be same. So now we go to the spec part. Here we define the actual container configuration. This was the pod configuration. And as I said, pod is an abstraction above the container. So we need to launch the containers, right? For that, container should have some configuration. So this spec contains the container configuration. So there is another concept in Kubernetes called init containers and sidecar containers. So what init container does, let's say we want some tasks to be done first, and then we want our application to run. Let's say we have a Java application and we want the configuration, the conf file to be downloaded from somewhere else, get it ready, and then the application should run. So that is done using init container. So what init container does, before the main container runs, it is supposed to have some work done, and then only after this init container runs successfully, then only this container will run, right? And the other thing is called sidecar container. What sidecar container is, a pod can have multiple containers. So when we have more than one container running side by side, doing some works, doing some like running some processes or something that are needed, these are called sidecar containers. So we have a main container and we have another container running side by side with it, maybe helping it with some data processing or anything. That's called a sidecar container. So if we look at the configuration of the init container, it's taking an image of Alpine, the Alpine OS. I give it an arbitrary name. Here is the resource part. I give it nothing, but here in resource I can say that I set a limits of CPU, let's say 1000 millicore, and the memory to be, let's say, 1 GB, right? I can set these limits, but for now I'll not set it. But yeah, this can be set to restrict the application with the resources. Now this is the env. So this is the name of the env, and here I can directly give it a value. Let's say value is hello, right? but I can also use custom configurations or secret to get this. So value from secret key ref and the key and the name of this. So I'll explain this later when I go through the config map and secrets. I show you those YAMLs. So here is a volume mount command and args. So what volume mount is, I have a volume called image dir and I want to mount it at a path called var images. Now here is the command and args. So these are basically equivalent to the entry point and CMD in Docker, which we went through in the previous session, right? So command is the entry point and args is the arguments. So I say that I use the shell and I run these commands. I install wget, I download a image and I make it executable. Right, so that's the task of the init container. And where do I store it? Var images architecture.png. So this var images directory is already mounted to a volume, right? So now I go into the main container. Here I have a sample image that I created. I give it a name, the resource, the image pool policy. This image pool policy denotes like when this image will be pulled. If it is always, so if the pod goes down and comes up, so every time this image will be pulled. This can be if not present. It means that if the node on which application is running has the image already present, it will not pull it. So I'll keep it as always. This is the ports, the port on which the application is running. So I say that on port 80, this application is running. Now we have a probes. So the application is running, right? But Kubernetes needs to have some health check configured to see that is the application really running or has it like crashed or is it stuck. So for that we have health checks called probes. So what it will do, it will send a HTTP GET request on the root path on port 80, right? And initial delay seconds is 12. So what this means, once a pod comes up, it will wait 12 seconds for the application to start up, and then it will send the request every 10 seconds. So if it receives a OK response from 200 to 399, it will say that the application is healthy. Otherwise, what it will do, it will like poll every 10 seconds, and by default there is a field called failure threshold, right? So let's set it to 3. If we set it to 3, it will once it will send the request, it fails. After 10 seconds, it will send again, it fails again. And after 10 seconds, it will send again. And if it fails, so the failure threshold is 3. So if it fails 3 times consecutively, so the pod will be restarted. That's the uh, purpose of the failure threshold. Same goes for the liveness probe. So liveness probe, what it does, it denotes whether the pod will be restarted, and what readiness probe says if the pod is ready to accept traffic. Now here we have the env part, which I'll explain shortly, and here I have the commands and entry points. Here if I explain it, it's so here in the init container it downloads the image, and what this part does, it checks if that image is empty, or if that image is empty, or if it has something like it has any contents. If it is empty, it will exit, otherwise it will start the nginx. And here we have the same mount path var images, and here we have the volumes empty dir. So what empty dir volume is, it's a type of volume which can be shared between all the containers running inside a pod, and this is a ephemeral type of volume. Once the pod goes down, it will be restarted and this will become empty. But the purpose of this is, let's say init container downloads the image, right? It downloads the image. This image needs to be accessible by this container. So we mount it using the name image dir, and this name is the this equal to this, and this is the empty dir volume. So basically this volume is mounted on this init container and also here. So basically anything we put inside var images will be available to this main container as well as this init container. So this is what the YAML config is. Now, if I go to the config map, so in config map, I say the API version, the kind is config map, the name, and now the main part is the data. As I said, it's a key value pair with plain text. The key is the name of the property and the value, the name and the value. So now, if I want to induce these configuration into the application, yeah.
Fine, I think we've reached 3:30. 30 minutes past our time. So what we'll do, we'll continue with this tomorrow, and for tomorrow's session, we'll have your session completed tomorrow in the first few minutes, and then we'll proceed with tomorrow's session. It is already 3:30, and it's uh, I think it's taking a lot of time. We had some fruitful discussions today, so maybe that's why we've taken this much time, right? Uh, so what I'll do, uh, we'll carry on with this session tomorrow. Tomorrow is the second last day of this series, finishing on Friday. But obviously, we'll cover the details tomorrow as well. It's 3:30. So thank you everyone for joining. Feel free to provide us your feedback. Feel free to provide us any topics which you would have wanted to cover, but they are not covered as of now. And we look forward to see you all tomorrow as well. Uh, all right. So we'll take a break today. We'll see you guys tomorrow. Thanks a lot for joining. Thank you, everyone.
Thank you, guys. Bye bye.
Thank you.
Nice listening.